Hello students, in the previous class we have seen the relation between electric field and potential. In today's class we will read about the potential energy in an external field. So we have three cases to learn in this topic of potential energy in external field, where we will see the case of a single charge. Secondly, we will see a case of system of charges. And third, we will see the case of a dipole which is kept in the external electric field. Now we will start with the first case, and that is potential energy of a single charge. Here we are considering a single charge. Now what exactly we are doing is that we are bringing this single charge from the infinity to a given point specified in this space, which is having these external electric fields. In these external electric fields we have defined from where these fields are coming and why this charge is not playing any role in creating its own energy to that particular source of external field. Now we'll start up. We'll look into the matter and understand how these are generated and how the potential have relation with the external fields. Here we have concern with the potential energy of a charge or charges in an external field. Our main concept over here is the external one. What does an external electric field means? External electric field is the field which is not due to the charge Q1. External electric field is field produced not by charge Q1. Instead, this external electric field is coming from some unspecified source. This unspecified source is also unknown to us. We do not know where this source is present, what is the magnitude of this source, but by looking into the electric field and the potential of this unspecified source, we can determine its polarity at the least. The external field E is not produced by the given charge or charges whose potential energy we wish to calculate. E is produced by sources external to the given charges, unknown and unspecified. What is specified is the electric field of E or the electrostatic potential V due to the external sources. How can we say that electric field or the electrostatic potential is specified? So we will take one example here. We will try to understand how this source is unspecified and unknown to us, but its electric and the potential are known to us. This is our system. This is our system or our space under our consideration, and we are having our charge here Q1, and this is some charge over here. We will take this as Q, unspecified or unknown to us. This charge is big enough. This charge is big enough to produce strong electric field which are coming till this point. Till this point. When we say this is our space, this whole area is our space. This whole area is our space and it is big. This space is big. Here we can have one charge and many charge. We can have many charges. So for us, when we look according to the charges, this space is very big and this distance is extremely big. This distance is extreme large distance. So one observer standing here, if wish to see till this point, will not be able to see. We will not be able to see this unknown or unspecified charge because it is extremely far away from our view, from our sight. So we told to everyone that this charge, which is producing extremely large electric field and electrostatic potential, is a unknown charge. But as this is big enough and it is producing these electric fields till over here, then there will be some interaction of these fields with our charge Q1. We know that electric field definition is given on the basis of the electric field lines. Secondly, we define electric field as Q upon 4 pi epsilon naught by r square. Secondly, potential is defined as QE. So here this Q is unknown. From unknown we are getting these electric field lines. So this Q is unknown, but for finding the potential at Q1, this electric field and Q1 are multiplied. So we are getting our potential. So now with respect to this potential at Q1, we are able to find electric field or vice versa. If we are aware of V or E, any of the two, and if we are aware what sort of charge our system is having, we can find the other property. If we know E, electric field, we can determine V, and from these two values we can determine the value of force, we can determine the work done, and hence we can know how much of potential energy is being stored by charge Q1 in the system. So that is the principle we are following up here to understand these all properties from the external electric field from an unspecified or unknown distant charge. Okay, so we'll go on to the next point over here. Just a minute. Yes. Now we assume that charge Q1 does not significantly affect the sources producing external field. So this is again one of the very important point. It says that if we are considering that unknown charge, unknown source of external field is producing such sort of effect on our charge Q1, then why not our charge Q1 is producing any effect on this unknown charge, unknown source of external electric field? Then first thing, there are two concepts. First thing is that Q1 is insignificant or it does not significantly affect. So we will write it in a small way that our Q1 is insignificant. It do not have ability to produce such strong effects which can affect the external source of electric field. Secondly, Q1 is big. Q1 is big and significant, but external source, I'll write over here, external source for producing E external is held to its position by unknown forces. So see, we are two human beings, one is child and one is adult. If we take the case, there are two human beings, one is child, one is adult, and this child pushes the adult. What will happen? Child will not have enough energy to push the adult and make the adult fall. First case is this. Child do not have strength as compared to the adult. Now the second case we are having is that in both the case, either the human under consideration is a child or a adult. Both are having same energy and power. So now this child is pushing this child, the other child. Child 1 is pushing child 2. Now what will exactly happen is that this child will fall. Because both are having same strength. If one is pushing other, the other will definitely fall. But in case behind this child is standing his father and supporting this child, and this child is now pushing again. What will happen? Now the C2 will not fall. Why? Because there is a support which is like having more strength than child 1. Child 2 plus father of the child 2, both are having their summed up energy which is greater than the energy of child 1, and hence we are not seeing any sort of effect on child 2. So the child 2 is not falling. So these are the two conditions in Q1 and our unknown charge which is producing these unknown external electric field. First thing, Q is insignificant. Q is very small. It do not have strength to produce that much of effect on the unknown charge. Secondly, Q is big and significant. It's producing external, like it's producing electric field in such a way that it can affect the external source, but that external source is held by some unknown forces to its position. So this unknown charge is not getting deviated, and it is producing the same sort of effect in both the cases. Now we'll move next to the point. Next point is that this is true if the Q is very small. Now if we take Q to be very small, this is true. Or the other thing which can be there is that external sources are held fixed by other unspecified forces, or the other is unspecified forces are playing their role in making sure that our unknown charge is not having any problem and is producing the same external field, though the charge, our known charge, charge Q is big enough. Even if Q is finite, its influence on the external source may still be ignored in the situation when very strong sources away from, definitely away at infinity, produces a finite field E in the region of interest. So in case our Q is big and producing some E, but this unknown Q is producing E external which is extremely bigger, in such case, though E is big, but E external is bigger, in such case this can be negligible, this can be ignored. The external electric field E and the corresponding external potential V may vary from point to point, of course, because E is defined on the basis of 1 by r square and V is defined on the basis of 1 by r. Both are having a direct relation with the distance between the two charges, whether specified or unspecified. If the position is changed, definitely we will see a change in electric field as well as electrostatic potential. Now, by definition of potential at a point P, we can say that work done in bringing a unit positive charge from infinity to the point P gives potential for it. How much work we are doing? How much work we are doing to bring any charge, any point positive charge from infinity to a given predefined point, that will be taken as potential. See over here, potential equals to work done to bring a point positive charge from infinity to point P. Okay, why we are bringing it from infinity? We can bring it from anywhere, but at infinity we are taking u to be equal to 0. Our potential at infinity is 0 and P is a predetermined point, and we need to define. Instead of P we can write R, Q, S, A, B, anything, but that is just for a point we are naming for our understanding. Now, potential at infinity is 0, as I have already stated. We always define potential for a charge, which is potential for a charge which we bring from infinity to a predefined point, because at infinity we assume potential for the charge in consideration to be 0. That is one reason. Now, work done in bringing the charge Q from infinity to point P in the external field is given by QV. Work done equals to charge into potential. We have seen, like in the previous class we have read, for defining potential for a single configuration, for 3 charge configuration, for 4 charge configuration. Under that topic we have seen how work done is defined. It is given by the charge under consideration and the potential we have got by bringing that from infinity. This work is stored in the form of potential energy of charge Q. Now, they come into this system from this infinity to this particular point P, the charges come. So, we have done some work along the path. In this path, this work, whatever is done, is stored in this charge. Now, you are traveling from a station, or we'll say from Hyderabad to Delhi, and your parent have gave you some pocket money. While traveling from Hyderabad to Delhi, what exactly you did is that you save that money. So, in whose pocket that money will go? That money will be in your pocket. You are never going to return it back to your parents because you have saved it. You did not buy any snacks there from the railway station. Instead, you preferred whatever your mother packed for you. And so, you saved that money by controlling yourself, and that money belongs to you. So, the amount of work done in bringing this charge from infinity to point P it will be stored in the form of potential energy, and this potential energy will be stored in the charge for our charge. Okay. So, that pocket money will be saved in form of savings for you in your account or in your piggy bank, anywhere like that. Now, if the point P has position vector r relative to some origin. We are defining this position r with respect to some origin. This is the distance we have taken, and this is some origin 0, 0, 0 we have taken. From here, from this particular point, this point is r distance away, r centimeter, r meter, like r units away. Now, potential energy of Q at r in an external field will be given as V of r. Potential energy at r, V of r. This is spoken as V of r. That implies V at r. External potential at point r. Now, this is the way we have defined external, in the external field, potential energy, which is given as QV, that is the work done, and as this V is defined at position vector r, V into r, sorry, QV of r, QV of r will be written. Now we have taken one example here, which will give us a numeral understanding of the potential energies. We have considered one electron in the system. Instead of charge Q, we are bringing a electron in this system. We are bringing an electron. So one thing everyone should know is that electron, proton and neutron are basic components, are undivisible components of an atom. This one orbits around nucleus, and these two are part of nucleus. They have their own mass and charge. Mass and charge. So, mass of electron is very light, is smallest. Mass of proton and mass of neutron is same, approximately same. Mass of electron is given as 9.1 into 10 to the power minus 31 kgs, whereas mass of proton and neutron broadly can be written as 1.6 into 10 to the power minus 27 kgs. As I say broadly, that does not imply that this is the exact numeral value. MP is something like 1.628, and this is MP's value, and MN is heavier than proton, and it is around 1.6 into 2, sorry, this one is 6 and this one is 8. Like they have very minute difference, but there is difference of the masses. Mass of proton is lighter than mass of neutron, and mass of electron is extremely lighter than mass of proton or mass of neutron. Now we will go with the charge. Neutron is told neutron because it is neutral. Neutron is neutral, so charge on it is 0. Electron is so called electron because it is negative, and it have a value of minus 1.6 into 10 to the power minus joule, 19, okay, so coulombs. Now mass of proton, it is positive charge, and it is written as plus 1.6 into 10 to the power minus 19 coulomb. So electron and proton are having same charge, only the difference is the polarity. Only the difference is their polarity. Now in this situation, we have considered a electron. Okay, we have considered a electron whose charge is 1.6 into 10 to the power minus 19 coulomb, and this should be having negative polarity. Now this charge is brought from a point to the point P and is accelerated by a potential difference of 1 volt. Is accelerated. Okay, we have brought it fastly, so the acceleration provided is of 1 volt. Now energy gain during this acceleration is charge into the acceleration. Charge into the acceleration of potential difference. Charge is 1.6 into 10 to the power minus 19 that's and into 1 volt. I will write it here. This is like the steps are not clearly mentioned. These are written in single step. I will explore these steps so that you understand how this answer we are getting. Okay, see. We are bringing our charge from somewhere, and this charge is our electron having a value of minus 1.6 into 10 to the power minus 19 coulombs, and the potential difference is given by 1 volt. Now we know that to understand amount of energy stored, we multiply charge with the potential. We multiply charge with the potential. It will be 1.6 into 10 to the power minus 19 into 1 volt. This is in coulombs, this is in volt. Now when we multiply, it will be 1.6 into 10 to the power 19 coulomb volts. Now this CV equals to joule, coulomb into volt equals to joules. So it will turn out to be 1.6 into 10 to the power minus 19 joules. Now another thing which we know is that 1 electron volt energy or the potential for 1 electron, that is given as 1.6 into 10 to the power minus 19 EV. Now if we multiply it with this one, we will find that the potential energy that is stored is 1 electron volt. Potential energy in dimensions of electron volt is 1 electron volt. So from this we can define the 1 electron volt of any charge. This is a concept which we will study in the further chapters like atoms and nuclei. These topics are common in atomic physics, nuclear physics and particle physics, where we deal with these microscopic like values or the microscopic parts of our atom. Mostly here we are dealing with the bigger world, so we do not aim at understanding energy in the form of electron volt, but this electron volt is defined as like amount of energy for bringing a charge or electron to some point by accelerating it to 1 electron volt. So in this case, this is how it is defined: amount of energy for bringing the electron from some point to the predefined point by the acceleration produced by the potential difference of 1 volt. Now this gives us electron volts definition, and this is how we define, and they are used for this smaller world, for microscopic studies or the atomic studies So clearly we will read it when we will start with atoms and nuclei chapter. Now we do not have just electron volt in our studies. We have kilo electron volt, mega electron volt, giga electron volt and tera electron volt. Okay, kilo, mega, giga and tera. Okay, so kilo is 10 to the power 3, mega 10 to the power 6, giga 10 to the power 9 and tera 10 to the power 12 electron volt. mostly bigger energies like energies of gamma rays and X-rays are defined in MeV, mega electron volt, and far X-rays and UV radiations, their energy is defined in the form of kilo electron volts. If we go lower to the visible and infrared, these energies are defined in in electron volt only. So this is as per to the electromagnetic spectrum. Electromagnetic spectrum. In the electromagnetic spectrum, highest energy is shown by the gamma rays and X-rays. These gamma and X-rays are defined in the terms of mega electron volt. So that's all for the today's class. In this class we have understood the relation of potential and electric field, and we have understood how external electric fields are used to define like the system in which the charge and electric fields are playing role, what is their effect, what is the effect of external electric field. Then we have seen one example of electron where we have defined its energy gain when we have brought our electron from some point to the point in the space we defined with a acceleration using a potential difference of 1 volt. We have understood 1 electron volt, and we have got to know that we do not define energy just in horsepower and joules. We can define energy in the form of electron volt, in the form of voltages also, and these electron volt energy definitions are mostly used in atomic, nuclear and particle physics. Here we do not basically deal with the microscopic world, but our whole macroscopic study of fields and potential are dependent upon the microscopic charges. Now in the next class we will read the same concept but for a system of charges. In the next class we will define a system of charges for the given external electric field from an unknown unspecified source. So that's all for today's class. We'll meet in the next class. Have a good day. Bye bye.